Okay, here's a problem solving video for problem 2.46. It says find Ix, and we're going to be using the problem solving strategies on page 41 and 53. If you look at that circuit, you will note that all of those elements are connected in parallel. There's only two nodes. So this is a single node pair circuit. The problem solving strategy is on page 41. The problem solving strategy on page 53 it deals with dependent sources. So let's start with the strategy on page 41. The first step says to find a voltage between the two nodes in the circuit, and we can pick the polarity, and I'm going to select the voltage V1 with that polarity. That's the voltage across every element in that circuit because we're in parallel. We have a single node pair circuit. So that satisfies step 1. Step 2 says, using Ohm's law, define a current flowing through each resistor in terms of the defined voltage. So if we look at our circuit, then the current using Ohm's law in this direction is V1 divided by 2K. Then the current is V1 divided by 5K through that resistor, and then V1 over 10K. So that's step 2. Using Ohm's law to find a current flowing through each resistor. Now apply KCL to one of the two nodes, and what we'll do is let's apply KCL to this top node. And if you look at the problem solving strategy on 53, it says when you write that KCL equation, treat the dependent source as though it were an independent source. So let's sum currents leaving the top node. So if we do that, we start here. This 10 milliamps is entering, so we'll have minus 10 milliamps. We'll have minus 2Ix, because that current is defined into the node. Then we'll have V1 over 2K plus 3 milliamps plus V1 over 5K plus V1 over 10K equal to 0. So there's KCL for that top node. Now let's plus 1 over 10K minus 2Ix is equal to 7 milliamps. So that's just collecting terms. Now, the second step in our problem solving video on page 53 says, write the equation that satisfies the relationship of the dependent source to the controlling parameter. So if I look on the diagram, I see where Ix is, and by applying KCL at that connection, I can write an expression for Ix. So from the circuit diagram, Ix is minus V1 over 5K minus V1 over 10K. So that's applying Kirchhoff's current law at that connection to come up with that expression. So now let's substitute that in. So we'll have V1 times 1 over 2K plus 1 over 5K plus 1 over 10K minus 2 times minus V1 over 5K minus V1 over 10K is equal to 7 milliamps. And if we rearrange, we'll have V1 is 1 over 2K plus 3 over 5K plus 3 over 10K is equal to 7 milliamps. Okay, now let's multiply that equation through by 1,000. So multiplying through by 1,000 gives us V1 times a half plus 3/5 plus 3/10 equal to 7. That gives us V1 times 14 over 10 is equal to 7, or V1 equal to 5 volts. So we picked the right polarity. Okay, we picked the right polarity. Now, back on the previous page, you can see the expression for IX that we derived by applying KCL at this connection. So now let's use that connection. So IX is minus 5 over 5K minus 5 over 10K. So minus 1 minus 0.5 gives us minus 1.5 milliamps for IX.